All right, so let's look at now, it's actually sort of three fundamental results. Cauchy estimates, Liouville theorem, and the fundamental theorem of algebra. So subsection 3.3.4 in the book. So basic idea is that now we have all the tools we need to have these three fundamental terms just pop out immediately as very short proofs, like one implies the other, right? So first, we'll just take the integral formula and the coefficients of the power series, right? And we'll just do the stupidest estimate that we know, just the triangle inequality on this integral, and we obtain the so-called Cauchy's estimates. Once we have those, then these estimates imply Liouville's term. Now, Liouville's term says that any entire function, meaning a holomorphic function, is defined on all of C, on the entire complex plane. If it's bounded, then it's constant, right? So it's a very sort of striking, simple result, right? There is no non-constant bounded entire functions. Liouville's term, in turn, implies what seems like maybe it's not a theorem of complex analysis at first, the fundamental theorem of algebra. Every non-constant polynomial has a root. Well, it is actually a theorem of complex analysis. It really makes complex analysis work, and it is this is the best known proof for it. And there's a whole bunch of proofs for the fundamental theorem of algebra, but usually, this is the most common proof of this result. And I would actually really say, it is a theorem of complex analysis, not as much of algebra. There's a lot of things that we do that are basically, underneath everything. It is sort of, this idea that you can solve polynomials, and that's how we started in the in the book, right? Defining complex numbers, right? We defined it so that we could solve z squared plus 1 equals 0, right? And so this says that, well, once you've added I, you can solve any polynomial. All right. So Cauchy's estimate. So for this, we need a little bit of notation. So supremum norm or uniform norm of a function over generally this would be a compact set K is just the supremum over that set, right? So if it's compact and we have it's continuous. So we're going to be looking at holomorphic functions, so they're continuous. So we're looking at the supremum of the modulus, right? So that's just notation. All right. So Cauchy's estimates are the following. We have an open U, holomorphic F on U, and we have a closed disk that's inside U, right? So it has to be, including the boundary, it has to be inside U. Now, we expand this function f in a power series around this point P, that's the center of this disk, right? So that's where we're expanding, right? Now, once we have that, we look at the formula for Cn, right? And we do a little bit of estimation, and we find that, well, Cn, or another way of, we've saw that those are equal to this, right? So we know that these are sort of equivalent guys. That's what we proved when we looked at analytic functions. That this number, whatever the coefficient is, so either you're looking at the derivatives at a point or you're looking at the coefficients of the power series, it's bounded by the maximum of the modulus of f over the circle of radius r, right? The boundary of this disk, divided by r to the n. So you need r to the n over there, right? So let's see the proof of this, because it's well, sorry, I was going to mention this first before the proof. So in other words, if you have, when we looked at power series, right, we said that basically, the convergence is the same thing as looking at the boundedness of these sort of sequences, right? That was one of the convergence tests for power series, right? So, all right, so we had that this is bounded. Well, now we know exactly the bound. It's actually the maximum of the values of the function on this circle of radius r. So now you know what that bound is, right? We're not just saying that it's bounded. That's what this bound is. All right, so let's do the proof. So let's take what was the formula for Cn? Well, it was this guy, right? That's from when we did the expansion of a power series, right? That's the formula for Cn. All right. Well, so we just take the absolute values and we estimate inside. You take the absolute values inside, right? Down here, because P is the center of the disk, so zeta minus P, that's just, the modulus, that's just R, right? So I get R to the n plus 1. And on top, I get, I had the modulus of F, and I'm going to bound it from above by its supremum, right? So all in all, we get this integral over here. And now what you notice is that this thing inside, right? This function inside does not depend on zeta, right? No longer, does not depend on the t once you parameterize the circle by some t, right? So you can just compute this integral, right? I mean, it's just a constant inside, right? And what you get is you will get 2 pi r, right? Because it's the length of this circle, right? Because this is the right. When you stick the absolute values inside, right? They also must go on the measure, so it's no longer just the d zeta. It's the arc length measure, right? The absolute value of d zeta. So the integral is 2 pi r because it's the circle of radius r, right? And so that r cancels one of these r's, and you get r to the n over here. All right. So fairly simple. So it's sort of the most obvious estimate, right? So let's look at an application. Oh, well, sorry. Let's look at before we look at an application. Let's look at that. This is actually the best estimate that you can get, right? You cannot get really a better estimate unless you know something else about the function. And for that, well, let's look at an example. So we look at just this polynomial, right? Some m, right, divided by r to the n, z minus p to the n, right? Now, m, well, if I look at the points on the circle and look at the modulus, right, I'm just going to get r to the n here, to cancel out this r to the n here, and just get m, right? The modulus is actually identically m. So its maximum is m, on the circle, right? But the Cn, right? Well, that's precisely this guy, right? It's defined as that, right? All the other coefficients are 0. There's only one non-zero coefficient. That's what it is, right? That's precisely this guy in the estimate, right? So we have this is supposed to be less than or equal to this, and here we have an equality. So you cannot get better than this unless you know something more about the function. All right. So let's look at this application that I'm promising, right? So again, just just to repeat, a holomorphic function is entire holomorphic function, whatever, more, explicitly, but we're just going to call them entire. Whenever it's say entire, it's just going to be a holomorphic function defined on the all of C. Examples, polynomials in Z, right? The exponential, sine, cosine, but not 1 over Z, right? Because that's not defined at the origin, right? So that's not an entire function. So now we have Liouville's theorem. A bounded entire function is constant, right? So a very striking, very simple statement. Okay, so suppose f is an entire function and it's bounded, right? So we have a bound for, on the modulus for all z. Okay, expanded at the origin as a power series, right? I mean, you can expand it around the origin, and this power series converges everywhere because the function is defined in all of C, right? And we know that the power series is going to converge in any disk around 0 that's inside the domain, and that's any disk, right, of arbitrary radius. So, right, that's just what I said, right? F is homomorphic on a disk of arbitrary radius, right? The power series converges on a disk of arbitrary radius. But mainly it's holomorphic, so I can apply Cauchy's estimates, right? And Cauchy's estimates say that the value of the Cn, right, the modulus of Cn is bounded by this m over Rn, right? Because this is what the Cauchy's estimate is, right? But whatever this is bounded by m, right? So I have that the coefficient is bounded by this thing for all r, right? Now, if we let r go to infinity, right? If n is not 0, if n is 0, then it's right. R to the 0 is 1, so nothing, right? But if n is 1 or greater, then r to the n goes to infinity, therefore 1 over r to the n goes to 0, right? So that means that Cn has to be 0 for all n bigger than 1, bigger than or equal to 1, right? That means that there's only one coefficient left. It's the C0, right? We can't say anything about that. But, that means that F is just C0, right? I mean, it is this series everywhere. And therefore, it's equal to just the first coefficient, right? So it's constant. All right. So fundamental theorem of algebra, right? We're on a roll, right? We can just prove. Well, this is the third one that we're going to prove today, right? So suppose that we have a non-constant polynomial, then we're saying then it has a root, right? And basically the idea is going to be to prove that if it doesn't have the root, then it's constant, basically, right? So let's suppose that P does not have a root, right? There is no Z for which P of Z is 0, right? Well, then 1 over P is a holomorphic function. It's an entire holomorphic function. Because if it didn't have any zeros, right? Well, then 1 over P is defined at every Z, and it's holomorphic, right? So now first, if P is constant, then R is bounded, right? If P is non-constant, then you guys have proved before that means that the limit of P is infinity, and therefore the limit of R is 0, right? So R is bounded. Now Liouville says that R, and hence P, must be constant, right? So it's almost immediate, right? So it's just, and then we got 3 sort of fundamental results. Well, maybe one of them, almost seems like from a different area of math, but this really is complex analysis. All right, so that's that's it for this lecture. So let me try to stop that. Oops.